Welcome back. In this session, we will see the design of FIR filters. Alright, let's start. So, first, let me tell you the steps that are used to design an FIR filter, and the technique that we will use to design the FIR filter is referred as the windowing technique. Alright, let me illustrate this technique to you step by step. So, the technique that we shall use is the referred as the this windowing technique, and the steps for designing these FIR filters. Let me illustrate. Now, first step in designing these FIR filters is in this windowing technique is you will be given some desired filter response. So HD omega will be given to us. So HD omega means a filter response is given to us, right? So this will specify what is the cutoff frequency, whether this is a low pass, whether this is a high pass, whether this is a band pass. So what do we mean by frequency responses if given to us? This means this will tell us whether this is a low pass filter, this is a high pass filter, this is a band pass filter, or this is a band stop filter. So this will inform us, and this will inform about the cutoff frequencies, right? This will inform us the cutoff frequencies of these filters, and this will tell us the magnitude of the pass band, etc. Alright, now let me give you an example of what I am saying. I'm saying if suppose the desired filter response is the low pass filter response like this, means from omega 1 minus omega 1 to omega 1, the response of the desired filter should be like this. This is the filter I want. I want to have the filter that has the response like this, right? So these will be the specification that will be mentioned. So it will be said that the desired response filter is non-zero from omega minus omega 1 to omega 1. Design this filter, and this is a low pass filter. We can check this is a low pass filter. Now we have run both negative and positive frequencies for this, but our aim is to design an FIR filter. All right, so remember that our goal is to design an FIR filter. So what is the second step? What is the second step? So this is the desired response that's given to you that we want to have, right? In the second step, we obtain HD of n. What do we mean by HD of n? This means the inverse discrete Fourier transform of HD of omega, right? So how do we do that? We know that discrete Fourier transform, that is h of HD of omega, will be given by this. If you remember the discrete time Fourier transform, it is power minus j omega, right? But this time this is given to you, so you have to compute this. How do we do that? By using the inverse discrete Fourier transform. So we say HD of n is equal to 1 by 2 pi integral minus pi to pi, as we know the maximum frequency varies from minus pi to pi, h d of omega e raised power j omega m d omega. So we integrate this expression with this given value of this and obtain h d of m, right? Now, if suppose this is the filter response, so if this is the desired response, now you can see the HD of m will have an infinite duration. If we take that an example, this will have an infinite duration, right? This will have an infinite duration, but we are not designing infinite duration filters. We are designing FIR filters, means finite duration, right? So how do we solve this problem? So the third step that we do in designing this is we truncate this. HD of m. So what we do, we truncate this HD of m. We truncate this HD of m for some limit. For example, we say from 0 to m minus 1. There are how many samples of this? M samples. So we retain m samples of this HD of m. Alright. Now, mathematically, how do we do that? So if this is HD of m, then we say h of m. That is our final filter frequency response, impulse response will be this, and we multiply it with a window that's called a window that will Suppose that's a rectangular window, so we multiply it with like this. We say this rectangular window has duration of how many samples? M samples, and rest of the samples are 0. So we multiply Wn with this HD of n, and we get the finite duration impulse response of our desired filter. Alright, so these are the steps. Alright, let me illustrate these steps. Let's take an example. Alright, let's have an example to illustrate these three steps. So these are the three steps that we'll stick on. So let's solve an example for this. Let's suppose the desired filter response that is given to you is like this. It is equal to 1, then omega is between, let's suppose omega is between minus pi by 4 to pi by 4, and it is 0 otherwise. So this is the desired filter response, and our goal is to obtain on this 10 obtain a FIR filter that has a size of 10 samples, means m is equal to 10. That's what you have been told to do, right? All right, so what we will do, we'll do here, we'll start with the this desired this response. So we'll start with this desired frequency response. So this is saying that this is equal to 1 minus pi by 4 to pi by 4, and rest of the values of this HD of omega are 0. This is the meaning of this. So you can plot it like this. So this is the first step. So this is the first step. Second step is what do we do in the second step? We take the inverse discrete time Fourier transform of this. We say it should be omega. This is the inverse discrete Fourier transform of HD of omega. Now substituting the value, as you can see, the HD of omega is 1 for minus pi to pi, so pi by 4 to pi. So this will, limits will change, and the value is 1. J is for omega dmx, right? So integrating this expression, what we'll have 1 by 2 pi e to the power of j omega n divided by jn. Why jn? Because we are integrating with respect to omega. So it should be minus pi by 4, pi by 4. So substituting the limits, this will be e to the power of j omega, sorry, not omega, because omega is the variable here. So this is e to the power of j pi by 4n minus e to the power of minus j pi by 4n divided by gn. Now what I will do, I will write pi here and n here and 2 here. Right, so this is our h of n, and we can write it as pi n. What is this? This is sine of pi by 4. So this is sine of pi by 4. And so the impulse response of the desired filter is sine pi by 4 and divided by pi. Now you can see this has an infinite duration, right? This has an infinite duration. That's why what we do in the third step, we truncate this. And we have been told that the size of this filter should be n equal to 10, means from 0 to 9. So what we will do, we will multiply HD with Wn. What is Wn? Wn is equal to 1 when n varies from 0 to 9, means n minus 1. N minus 1 is 10 minus 1, that's 9, right? So n, which is 0 otherwise, right? So 0 otherwise. You can plot it Wn also. You can say Wn is equal to 1. So this, so from 0, 1, 2, 4, 9, 10, this is our Wn. The rest of the samples are 0, and we multiply this Wn with Hdn, and we obtain the response. So H of n is equal to Hd of n multiplied by Wn, right? Wn. All right, so hd of n is sine of pi by 4m divided by pi n times w. Now, you have to compute the values of this. So what you will do, you will write the values like this. So these are the values of m, these are the values of hd of m, these are the values of w n. Then you will see the values of h of n, which is equal to hd of n multiplied by w n, right? So you will try to get the value. So from n is equal to 0, hd of n, you can get the value. So hd of n, what will be hd of n? We check it. I think it will be uh, minus sine pi by 4 0 divided by pi by n. Huh? Yes. This will be sine pi by 4m pi by n. So when n is 0, this will be 0 by 0 for m. So hd of n is equal to sine pi by 4m divided by pi. Now when you put n equal to 0, what's hd of n? hd of 0 is 0 by 0. So how do we solve this one? Indeterminate form. How do we solve this? By using L'Hospital rule. So by using L'Hospital's rule. How do we resolve this? We say hd of n is differentiating this. This will be cos pi by 4m divided by pi. We are differentiating with respect to m. So this will into pi by 4. So pi by 4 pi. So the value hd of m, put m equal to 0, this will be cos of 0, cos of 0 is 1, so we have 1 by 4. So the value at n equal to 0 is 1 by 4. And this is 1, so the value of this will be 1 by 4. Now put n equal to 1, so we have to get hd of 1. How much is hd of 1? Sine pi by 4 into 1, that is 1. Sine pi divided by pi. How much is sine pi by 4? That will be 1 by under root 2 times pi. Please check this value. Please check the value. And sorry, this is 1. This is 1. And so the multiplication between these two pi by 2. And we are multiplying these two. Then you get 2. Get the value. Then put n equal to 3. Get the value. Right? Put n equal to 4, get the value, so on up to 9. So on up to 9, and get the values of this. So this is our finite FIR filter by using the windowing technique. Using the windowing technique. Alright. So this is one way, one window that we can use, right? So what we did actually, we obtained the impulse. There's a impulse response of the given desired filter, and then we multiplied this by the window, rectangular window, and we got our desired filter. We got our desired filter. Now let's think about this. What is happening simultaneously in the frequency domain? When you multiplied hd of m by w m, what's happening in the frequency domain simultaneously? Now we know our wm. Wm has a width of m samples. Let me generalize it. So it has a width of m samples, and the rest of the samples are 0. So I can write 0, 1, 2, 3, so on m minus 1, m minus 2, m minus 1, and mth sample is 0. This is m, and this is our w. And let's assume that the amplitude is 1. Now we have solved already this. What is w omega of this? Means what is the Fourier transform of this? Fourier transform of this will be simply summation n running from minus infinity to infinity Wm e to the power of minus j omega. Why I am doing? I want to check when I am multiplying these two sequences in time domain, what's happening in the frequency domain. Alright. So this summation changes like from 0 to n minus 1 w and e to the power of minus j omega. And now you can see this is 1. This is 1. And substituting the value, e to the power of minus j omega n, and we already solved this when we derived the discrete and transform of a rectangle window, if you remember, and this comes out to be, if you remember this, please have a look and try to solve it. I will not solve it here. M is the size of this rectangular window. Please check it. Divided by sin omega, and we have already plotted it there. So this is our, yes, alright. So this is our, this is omega, huh? This is omega. Alright. So this is the Fourier transform of this rectangle. So what you are doing to obtain h of actually you are doing h of n, that is equal to ht of n multiplied by wn, and the same operation in frequency domain will apply. So this is the frequency. These two will be convolved. So these two will be convolved w. Right? So you are convolving this function with that desired response. Right? So this was this was what this will be given to us. So this will be given to us, and we are convolving it. So this is one type of window. So this is one type of window, and this is the frequency response of that window. This is the frequency response of that window, right? So this is the frequency response. So what you are doing in frequency domain, you are convolving it. Same way, there are different type of windows. So there are different type of window. This is just a one rectangular window is one type of window. Is one type of window. So there are several type of windows. For example, some of these are mentioned below. The first type is Bartlett window. Bartlett window, or this is also referred as triangular window, right? And the WM, the window here is that's of size. I am assuming the size of these windows is M equal value from 0 to n minus 1. Then the Bartlett window is 1 minus 2 magnitude n minus n minus 1 divided by 2 divided by n minus 1. So this is our Bartlett window. So this is our WM. So this is our W. So when you multiply HD of M with this window with given M, you will get the this H of M there, right? Same way, if it was Blackman's window, we have one more window that's referred as Blackman window, and for Blackman window, WM is 0.45, 0.5 cos of 2 pi m divided by n minus 1 plus 0.08 cos 4 pi m divided by n minus 1. Right? Please check the values. Now another window that we have is the Hamming window. Hamming window, and the WM for this is 46 cos 2 pi m divided by n minus 1. And one more window that we have is the Hanning window. This is Hamming, this is Hanning, Hanning, and WN for this is 1 minus cos 2 pi and divided by 1 minus 1. Same way we have Kaiser window and 2K window, Ule and 2K. Okay, this is the name of the scientist, and these windows will have some similarly value of WN, right there. So what we do, so if it is asked to you, you are given some desired filter response, then what you will do, first step is obtain H of B of n, then multiply this with any of these windows, that is whatever is said to you, whatever is said to you. So you have to remember these windows. So whatever is said to you, you have to multiply these two and obtain the response from 0 to m minus 1. All right. Now in the next session, we'll continue with the discussion on the designing FIR filter.